For our next lesson on the functional group amines, we'll be looking at various reductive methods. This is an example of converting an aldehyde to a primary amine by first forming the oxime with hydroxylamine and then reducing it with lithium aluminum hydride. Another reagent that can be used is sodium cyanoborohydride. Okay, the advantage of this reagent is that we can do this all in one step because the sodium cyanoborohydride reacts faster with the oxime than it does with the aldehyde or ketone. Okay, if we use a ketone and a primary amine, we can couple those together to form an imine and then reduce that with lithium aluminum hydride. Okay, to form a tertiary amine, we can start with ketone, for example, react it with a secondary amine to form an aminium salt. And there's a special reagent that works for this. This is called sodium triacetoxyborohydride. And that adds a hydride to this carbon here. This aminium salt is frequently unstable, so they're not isolated. Okay, the previous two examples with the oxime and the imine, those can both be isolated. And then in the last step, we use a reducing agent to reduce the aminium salt to a tertiary amine. Okay, so here is an example of reductive amination. Okay, we start with aniline. We condense it with cyclopentanone. Okay, water is split out. We get our imine, and then we can reduce it. Another way we can reduce it is through catalytic hydrogenation. Okay, to form this tertiary amine, okay, one way we can do that is to form the aminium salt and then use this reagent, sodium triacetoxyborohydride. Okay, besides oximes and imines and aminium salts, we can also reduce amides. And if we do an acylation followed by a reduction with lithium aluminum hydride, we get a primary amine from ammonia. Okay, notice that when we reduce this, there's no alcohol group. In fact, there's no oxygen at all in the product. Okay, the oxygen actually binds to the aluminum. Okay, there's no tendency toward over-acylation. Okay, once we acylate this, it doesn't react a second time. Okay, if we acylate a primary amine rather than ammonia, then we can get a secondary amine as our product. Okay, then if we use a secondary amine as our starting material, we can form the amide and then reduce that to a tertiary amine. Okay, so here's an example of acylation reduction. Okay, we ultimately split out HCl, and pyridine acts as both a solvent and a base to neutralize the HCl. This gives us the amide, which we can then reduce to the tertiary amine. Okay, here we have the Gabriel synthesis. Okay, there's a step that has been left out where we have an H on the nitrogen. We would remove that, say, with potassium hydroxide or potassium hydride to form this resonance stabilized anion. Okay, this could then attack an alkyl halide to form the alkylated phthalimide. Then we react this with hydrazine, and we form the phthalhydrazide or phthalimide hydrazide and a primary amine. Another group we can reduce is the azide group. This will only produce primary amines. Okay, we can start with an alkyl halide or tosylate and then react it with the sodium azide. And that gives us an alkyl azide. Alkyl azides are explosive, so we don't want to isolate those. We want to reduce it as soon as it's formed. Okay, we can also reduce nitriles. Okay, again, this only gives us primary amines. And we can form nitriles by doing an SN2 reaction with a primary or secondary halide or tosylate, and then reducing it with lithium aluminum hydride. You can also use hydrogen and a catalyst. Okay, what it does, it adds 2 hydrogens to the carbon and 2 hydrogens to the nitrogen. We can reduce nitro compounds. Okay, back in our chapter on aromatic substitution reactions, we didn't really have a good way of introducing an amino group to a benzene ring, but we can readily nitrate benzene rings. And once we nitrate, we can reduce it. There's a couple ways we can do that. One is with hydrogenation, hydrogen and a catalyst. The other way is to use an active metal, tin, iron, or zinc, and acid. This is a method that's commonly used to synthesize anilines. Right, next we'll look at the Hofmann rearrangement as opposed to the Hofmann elimination. Okay, notice here that if we compare the starting amide with the product amine, we're missing a carbon and oxygen. Okay, that is actually given off as sodium carbonate. Okay, this is a complex mechanism. Okay, the first step is hydroxide removes one of these hydrogens off the amide. This could only be done with primary amides. The negatively charged nitrogen then picks up a bromine. Hydroxide removes a second hydrogen, okay, which is rendered even more acidic by the presence of this nearby bromine. And then we have an alkyl shift and a rearrangement. And this gives us an isocyanate. Hydroxide then attacks the carbon of the isocyanate. Carbon is between 2 strongly electronegative elements, oxygen and nitrogen. And we push a pair of electrons onto the oxygen. Nitrogen then picks up a hydrogen. We get a carbamic acid. Carbamic acids are not stable. And so the next step is deprotonation and elimination of carbon dioxide, okay, which will react with hydroxide to form carbonate. Okay, and then our negatively charged nitrogen picks up an H from water, and we obtain our primary amine with 1 carbon fewer than what we started with.